Okay. Right. So this is ring theory. We have all seen all the time that rings come in everywhere. I mean, when you're dealing with maps and so on. So commutative ring theory, right? It's what we want to do. Commutative ring theory. So what I will suggest is there is a chapter in Artin which is called rings. You should read up that completely. Yeah, try to do it. Put have effort and complete it. Rings. Okay, you can read it in details. And otherwise, you can also read chapter 1 of this same book called Commutative Algebra. I will just do chapter 1 today quickly. So in the sense that I will do it on a level which is the details will be not told, that so that you can read, so that when you read, you can read easily. That will be my goal. Okay. Just to give you an overview. And then all the principles and so on, principal ideas, special cases, those you can do. And yeah, but this is easier to read. And this is by Attia and McDonald. IG McDonald. So yeah, let us just do this chapter 1. So as I said, I'll do it abstractly. I will not do it with a lot of examples and so on. And but I will give you a picture of the landscape. Okay. So that when you're reading, you will know where the goal is and where you want to head. So you keep reading it. Yeah. So first is a ring, right? Definition of a ring. And obviously here the ring means a commutative ring. And so we will talk about those things. So what is this? So this is a set R. Okay. And this is an abelian group. Okay. So it has inverse and everything. And this is just as a multiplication with an identity, nothing else. Yeah. Is a commutative monoid. And commutative monoid just means it has a. So this just means that dot is a binary operation. I suppose you people already know it, of course. It's a binary operation and there exists an identity and it's commutative. Okay. Right? So A dot B is C and so A dot B is B dot A. There is a E such that this is just meanings of identity. And this is an abelian. So you see the commutativity is here. This is always assumed to be commutative for a ring. For certain reasons, it actually becomes commutative under very, even under very minimal conditions. So this is just a definition of a ring. Okay, and examples in integers, polynomials. And of course, there is a distributive law, which I have not said, but I should say, is a distributive law, which you know. I don't need to write what it means, right? Distributive law holds. Just what you expect. If I don't say the detail of something, it's mostly just what you expect, or I'll tell you that it is written point. So this, but the new player, which maybe you have never, which maybe you have never used, you have only seen in ring theory, maybe, is a ring homomorphism. Okay. Of course, you see that if you do some functional equations like Cauchy functional equations, so on, or special examples of that. But a ring homomorphism. So I'm not giving motivation and so on. I'm just writing the definition but telling you the landscape. Motivation will be in the language of ring theory only. So not going outside and with examples and so on. A ring homomorphism, so what is this? So this is a function f, okay, between two rings. Okay. It's a function between two rings, and of course, it's just a function which commutes with these two operations. Okay. What does that mean? commutes with these two operations, it means that you have the plus operation and it commutes, which means that you first apply the plus operation, then apply the function, or you do it the other way. This very much is like what happens in vector spaces. Right? But this is property number one. And property number two is that it commutes with the other operation. Yeah. This scope is not there for vector spaces, right? Because in vector spaces, these two, I mean, one of them is a scalar, so you cannot apply f on it. So, right, I mean, this is some nonsense, sorry. So it's not just a function, it's a morphism. It just morphs the ring, but it's still a ring. They're respecting certain things. This is it. And some people also write f of 1 is. So 1 is a notation for that identity. The identity in this, yeah, monoid. Monoid you can actually read on Wikipedia, at least to begin with, just read a small Wikipedia or something. Don't go into theory of it. Monoids are interesting as well, but they have some less structure, but they still are interesting, but a little more difficult to deal with because I would say sometimes a little more difficult. Okay. So ring homomorphism, this is going to be fundamental for us, knowing what a ring homomorphism is. And then there is a notion of a subring. So again, just to give you a landscape of what is happening, I am saying these things. So maybe I'll just say it so that we can come back if you need to. Yeah. Subring. So what is a subring? So it's a subset. Okay. It's a subset, and S is a ring under the same operation. This is important. If you change the operations, then it's not called a subring. Then it's a subset, which is a ring. But as a ring, it is not a sub. Right? There is a difference, right? I mean, you cannot just take, if you just take a subset and put some other operation on it, then that's not a subring. Yeah. So this concept is useful, but maybe not very useful in the beginning. But then we come to the important players, is the ideals. Right? And maybe, as he's saying, also quotient. Just a rapid view of things. So, ideals and quotients. So why are these two put together? You will see. What is ideals? Ideals are basically special subsets. Okay. So special subsets of a ring are called ideals, and they behave like zeros. They behave like zero. Zero is there, but these subsets are also like zeros. So what is it? So this is in R. So maybe ideal is just I only. The notation they have is A in this book, but we'll just quick type it. I think R10 has I. I is a subset of the ring. And as I've said earlier, so if A is in I and R is in the ring, then R dot 0 times anything is 0. So it's also 0, which means it's also in. Okay. See, these things can be motivated, but I will not saying it right now. It's in all sorts of ways, but it's important to know the definition so that you can start thinking in terms of these, and when you read, you can easily penetrate on the other level, right? So this thing is there, and of course, I is also a subgroup. I is maybe I plus. If you take the subset I and put the addition operation, then it's a subgroup, which just means it's closed under addition and so on. See, so this also means that if A is an I and B is an I, then AB is an I, right? But it's not a subring because it doesn't have identity, right? Doesn't have identity in general. If it has identity, then it actually has everything, right? If it has identity, then R is an I for all R. So then it's not interesting because if you make one zero, then everything becomes zero. So everything becomes in the idea, something like that. So that's why it's not a subring, and in this definition of ring where you want a unity. In some more general, but in our case, it's not. So this. Now the main play thing is the quotient rings. The quotient rings are very important because basically mathematics is in some sense what happens. Like it's like, you may have heard of this phrase, is the art of giving the same name to different things, right? When you do like triangles, so a collection of triangles. As kids, maybe you don't distinguish between two congruent triangles, but as you start to do mathematics, you formally say that no, these two congruent triangles we will say same. Why? Because for certain purposes they are same. So we start calling different things same, and this of course goes on and on. Modular arithmetic example and so on. So
So
quotient.
shouldn't it like be the other way around actually, like giving different names to s- like some things that are in essence the same?
In essence, they are the same, and then you want to give different names.
Yes, like I feel like there
Okay.
are many uh like we have different concepts, like on the surface they look like they're different concepts, but like when we generalize it and like make it more abstract, and then you realize no, they're like a consequence of the same thing. So something like that.
Yes, that's right. Yeah. So when you generalize, then you realize that they are the same, right? And so basically, right,
Yes.
and that generalizing is doing the mathematics, right? Right. So when you generalize, then basically you're doing mathematics, and then you're giving same name to different things. I mean, not a mathematical debate, but you understand.
Yes,
From
yes,
my point of view is that, for example, you see a ring of polynomials and then you see a ring of vectors. Yeah, some mathematicians did give them different names, okay, because they are different for some reasons. But what I'm saying, same name to different things, is that is realizing commonalities between different things, right? And when you realize a commonality between polynomials and vector spaces, you see that there is R3. You see that there is a commonality if you view them as vector spaces. So they are special cases of vector spaces, right? So mathematics is putting an effort into doing that, certainly, right? Is it also distinguishing things? Yes, certainly. I mean, it's also distinguishing things which are in essence the same. Yeah, certainly. Because why are you because you understand. Because when you want to understand, because when nature demands you to understand things in a more detailed way, if you want to understand the multiplication also, then you put different multiplications and then they become different, right? And then you give them different names which are in essence the same. But that's probably also correct. But I think the effort is to generalize, and that generalization is sort of getting the same name. But yeah,
yes,
but
yes, sir.
yeah, it's I think both ways. It's yeah. One realizes, one overdoes something and then underdoes, and then it moves on. So this is the notion of an ideal. So let's here only we can define the notion of quotient ring. It will be helpful if you have studied groups and quotient groups, but not necessary. So right. So you do this, right? You start with a ring, okay? Start with a ring and you put an equivalence relation, okay? Start with a ring and put an equivalence relation. So you put maybe I will just say that start with a ring. Okay. So let tilde be an equivalence relation on R, okay, defined by, we say that A is equivalent to tilde, okay, if and only if. So basically, we are saying that I is 0. We want to say I is 0. I is the new 0. So we say A is equivalent to A is equivalent to B if A minus B is in I. That is all. Okay. And then you look at R, the set R, and this is an equivalence relation you have to check. But then you look at the set R under this equivalence relation. Okay. Then this becomes a new set. And that set we defined as this. Under this equivalence relation means that this set, the elements of this set are parts of the partition created by the relation. Right? Simple example is you take Z and you fix some number, let's say 7. Then you say that A is equivalent to B if and only if A minus B is in the ideal of 7, which means it's a multiple of 7. 7 divides A minus B. 7 divides A minus B, then you call them equal, right? Then what happens? Then this R quotient lambda, this is a set. And what are its elements? Its elements are also sets, but they are now elements. 0, 7, 14. This is one element which we just call 0. You don't write the set. So this is the situation. Similarly, 1, 8. We maybe just call this 1. Take one representative and we call it. We represent that part by that thing and we think of it like a thing. We don't think of it like a set or something. I mean, yeah. So this is an example. So this is the quotient ring. This is called the quotient ring. Okay, R quotient I. Okay, so its elements are parts, but we think of them through the representative of the parts, right? We think of them also as elements, and they also become a ring, right? Because you can just add, but that I have to tell you how to add. Right now, just a set. I have to tell you how to add. Okay, so this is fine as a set, but then as I said, R mod tilde is a set, okay, set of parts, but it's also a ring. So if you take two equivalence classes, A and B, you can define I'm representing equivalence classes. This is equivalence class containing A, equivalence class containing B. These things is there. And then their addition, I mean, there is only one way to define it. Okay, this is the definition. Or maybe this is the definition. Okay. And similarly, you take this and you define it. Okay, but there are problems with this definition, which you have to verify, because now things are not, I mean, it's like, you see, so the problem is like this. I have taken this box A and box B, and I've defined the addition of these two parts as the part corresponding to the addition of the elements A and B. But then you may take some A prime, which is the same as A. Means the part is same. The elements are different, but the part is same. So small picture is A and A prime and B and B prime, right? So I've taken A and B and their part. This you can represent by box of A and box of A prime both. If you represent it as box of A prime, and similarly for B, you represent it as box of B prime, right? Then the addition that you will define, one definition will give you this, and the other choice of representatives will give you this. But how do you know they are same? That is not given, right? How you have to tell that this and this are in the same part. So that the part you get is unique, right? But that is easy. They are in the same part. What does it mean? It means that they are related. So you need to, so this is same as checking that A plus B is related to A tilde plus B tilde, which is the same as checking that A minus A prime plus, means I'm just directly writing, is in I. But that is true because this is in I and this is in I, and the sum is in I because it's a subgroup. Okay, things like these are needed to verify this. These things take a little bit of work depending on the background, but You work it out, and these things are worked out in RTN. They are not worked out in here. This is you have to do on your own if you read this RTM account. So it's fine, but mostly look. I mean, it's not as bad as it may look. Once you get comfortable, then you basically don't think of it like this. You know most things will work out, and you think ahead. And yeah, we find some properties of these objects, and we basically work with those properties. We don't work with the definition and parts, and that will quite some work. Okay, right. So we have taken rings, we have taken ideals of rings, we have taken quotients of ring by an ideal. So you don't take quotient of a ring by a ring. That's a nonsense concept. That doesn't work. That will not work. Okay. Yeah, you will see that it will not work. So the properties of ideal will be used in showing that quotient. Just like if you're in group theory or normal subgroups, you need that normality for it to work. But the one of the properties which I should state is the following, which basically it's called correspondence theorem. Again, you should read these things from Martin, but I'm telling you from the way I've told you, and I'll give you an example. Correspondence theorem. This is actually going to be one of the things which makes life easy. So they don't have to think about quotient ring as that complicated second order thing. The second order thing is like every element is a subset. But then what is the correspondence theorem? Well, the idea is that you look at a ring R, and then you look at a ring and you quotient by I. Okay? And now you know the ideals of R, let's say, or you look at the ideals of R, look at all the ideals of R, and then you look at all the ideals of R mod I. You want to study a relation between these two things. Okay? You want to study a relation between these two things. Okay? First, let's take an example, then it will be better. So you look at Z, and you look at Z mod 20, 20Z. So 20Z is an ideal, no problem with that, right? Something is a multiple of 20, then multiply with anything, still a multiple, so on. So you look at this ring. What are the ideals of this ring? These ideals of this ring, I'm just writing the set of ideals. So ideals would be what? Like the whole ring which is generated by 1, even numbers generated by 2, multiples of 3. These are all the ideals, right? Every ideal is like the principal ideal domain. And that is, I won't prove all that. That you can just read. It's very easy. Multiples of 4 and so on. Basically any number and then its multiple. These are the only ideals. That is what the theorem is. And that comes from the definition of ideal and Euclidean division. But what I want to tell you is the relation. Now come to this side. This is the interesting part. Right. What are the ideals here? What do you think? This, you have a working model of this also. This integers model. I mean, this is, you don't think of it as parts and so on. Just think of it as working just integers modulo 20. That's a ring. So what are the ideals of that ring? What are the ideals of that ring? So basically, you have to just maybe take some principal ideal. So if you take A in Z mod 20Z, let's call it Z20 now. If you take A in Z mod 20Z, and then you take its multiples, right? Take its multiples. Then Yeah, let's take an example and do better. So yeah, so you you take 20, right? 20. Sorry, you take 4. Okay. Then what will the ideal generated by 4 be in this ring? It will be 4, 8, 12, 16, 20, 0. And then you cycle back, right? So this is all, right? This is certainly an ideal, right? Any problem? No?
No,
This is
sir.
ideal. Right. Now, what happens if you take ideal generated by 8? Let's see. 8, yeah, 16. Then you have 22, which is 2, or sorry, 24, which is 4. And then again, 8, 12, 0. You get the same thing. The ideal generated by 4 and the ideal generated by 8 are the same, right? So these two are the same. Okay. So you can see some kind of pattern, right? That if the GCD of A and 20 is equal to the GCD of B and 20, then the ideal generated by A will be same as the ideal generated by B, right? And it is not difficult to see because the things which are not in the GCD, they are sort of invertible, because if the GCD is 1, then the ideal generated is all, because then you find an inverse, right? This would model everything. 3, the ideal generated by 3 is everything. So basically, it is in that way that this is happening. Okay. So then, if it only depends on the GCD, then what should we take as, then whose, so the ideals should that we take, ideal generated by single elements, what should those elements, what will those elements be that we should take? Just the divisors of 20, right? Because they just take the GCDs. The GCDs are divisors. GCD of anything to 20 is divisor of 20, and we just take those divisors and work. Because every other number, if the GCD matches, it will match with one of the divisors, and they don't have to do anything. Right? So basically, 4 and 8, you don't have to consider this thing. You just have to consider 4. 8 is not important. 8 cuts this thing is the same. So that's why you only consider the divisors of 20, right? And consider the ideal generated by them. Okay. So yeah, so the point of saying this was that the ideals of this, under this arrow which I'm drawing, the ideals of this are just divisors of 20. So see, 4 is there, and what are the divisors? 5 is there, 2 I missed, and what else is there? 10 is there, and 20 is 20 is just 0, a 0 ideal. So these are the only ideals, right? I mean, again, you can show that. I mean, you can show that it's a principal ideal and so on. Every ideal is generated by 1, and then yeah. Now you look at the picture. Right? Now you look at the picture. If you take, but I need to, right. If you interpret the ideal of this, now it's a new thing I'm saying. So this ideal of 4 in Z mod 20Z in integers modular 20. If you interpret this ideal in Z, interpret the ideal in Z, then what do you get? You get an ideal which is containing 20. Right? If this ideal you interpret in Z, right? If you interpret it in Z, then it actually contains the ideal generated by 20. Because of course, multiple will be 20. So all these are basically ideals that contain 20 or contain the ideal generated by 20. If you interpret them in Z, because they contain 0 here. Right?
Because each multiple of 20 shows.
Each divisor of 20 shows. Right.
Yes.
Yeah. So every divisor shows, and they are the only ones. And when you take the ideal generator, they will contain 20. Now this is what generalizes. Okay, that the ideals in this ring are in some sense matching with the ideals here. Which ones? Which contain 20, which contain that ideal which you are which you have which contain that one ideal which you're quotient by. Okay, that is the theorem. So how do you state it properly? So what you say is that I will go from here to here by a projection map. What is this? Just take the element and map it to the part where it belongs to. This is a partition, right? Z mod 2z is a partition of Z. Just take 2 and map it to 2. Take 22, again it will go to 2. And then, so this map, this first you show the pi is a ring homomorphism. Pi is and it's some in a way universal. I will also try to show some category theory point of view little later. It's not there in Atiyah McDonald also, but we will do it. It will be useful. So pi is a ring homomorphism that you should check, which we defined earlier. So it is one of those things. And now you see that the inverse image of any ideal J, inverse image you understand, right? Inverse image of an element, inverse image of a set under a function. This is an ideal that you should see. Okay, it's an ideal is fine, but this contains I. In this case, you see the 20 goes to 0, right? 20 goes to 0, right? So if I take an ideal here, you take a J, this is a J. If you pull this back, means what are the things that map to this ideal? So what are the things that map to 5? What are the things that map to 10? What are the things that map to 15? What are the things that map to 20, meaning 0? But what are the things that map to 0? 20. So that ideal, 20, 40, all of them, right? That's the inverse image. That's a subset of Z, right? That will always contain this ideal because this ideal is you made 0. And so any ideal here contains 0. So when you take the inverse image, it will contain I. Okay. So this is true, right? For every ideal, this is true. But also that uh, in this way you get all the ideals. Okay? Every ideal of I, you pull it back, you get ideal containing this, and also the other way. So let me state that. Yeah. So in this way, I have said the correspondence theorem for Z as said that Z and Z mod 20Z. So 20Z is the ideal. That the ideals of Z mod 20Z are basically the ideals of Z which contain 20Z, or it's basically the numbers which divide. Okay. So that is just what will generalize. That if you take this I, if you take this pi, okay, then ideals of R mod I are in 1-to-1, and it's a much stronger kind of correspondence, but right now we will just say this is in 1-to-1 correspondence with ideals of R which contain I, which contain I. Okay, and let me explain how this correspondence works. If you look at this direction, it is just pi inverse, right? Take an ideal here, take the inverse image of it. That will be an ideal in this, and it will contain R. That's clear because the ideal that you had here. So maybe I'll keep that. You take a J and you pull it back, pi inverse, right? And pi inverse J. This will contain I for sure because I goes to 0 and J contains 0. Every ideal contains 0. It's a subgroup. But the good thing is that if you go the other way, it's just by pi. But if you take the ideal which contains I, then this is a bijection. Right? Means you take an ideal here which contains I, you push it here, it will be an ideal Doesn't always happen. If it contains I, then it happens. Okay? You push it here, take the image. It's an ideal here, which is J. You pull it back, it's an ideal here, but that ideal is exactly the ideal you started with. That is also not doesn't always happen. It happens in this particular case when you take that ideal which contains I. Otherwise, it won't always be ideal. It won't always work. Okay. It's quite a theorem. I mean, this theorem needs a proof. It's a long theorem, but yeah. But that you should read from Martin. Not long actually. I mean, once you understand it and with examples, then it's fine. It's long because maybe foundations of set theory, foundations of functions, how good you are with dealing with those. Okay. So this is the thing. Next topic is zero divisors and nilpotent element, which are important. The units of a ring are important. These are the different kinds of subsets, which when you're solving problems, either you will see, okay, this is the nilpotent element, which was there in one of the problems, even linear algebra problem. Is it a zero divisor? Is it this? Then when you get hang of the correct class, then you can use theorems from there. But we will do it next time. So let's do it on Tuesday. Tuesday we meet, okay? And we'll continue with this, 8:30. But what you should do, okay, what you should do is certainly start reading Artin. Whatever chapter number from rings you should read, and you can read this book also. And please read, please, you have to spend some time. Today you have time. Read it. Otherwise you can not be able to follow. All right. We'll try to finish this chapter in 1 or 2 more classes.
Yes, sir.
Okay. That's it then. We'll see you on Tuesday. I'm ending it.